So for this lecture, we will be discussing the elastic lateral torsional buckling moment MCR for lateral and supporting beams. So as discussed earlier, we have two lateral support categories. First one is the continuous lateral support by embedment of the compression plant, which is done normally by pouring slab on the floor system of a beam column frame. And the second one is a lateral support uh, placed on intervals, or what you call the lateral brace beam. So we will be focusing now on this second category for this particular lecture. So the strength of I-shaped beams under uniform moment may be described in terms of the failure modes if mu is less than mp. So the first one is the local buckling of flange in compression. So the second one is the local buckling of web in flexural compression. And for the third one, we consider lateral torsional buckling. So these first two criteria on the failure modes are quite similar on the concept of plate stability analysis for compression. While the last is the failure brought about by the effect of lateral torsional buckling due to the insufficient support condition applied laterally to the beam frame. So there are four categories of behavior. First one is that the plastic moment strength MP is achieved with large deformation or rotation. The second one is the inelastic behavior where MP is achieved but with little rotation capacity. The third one is the inelastic behavior MR, the moment above which the residual stresses cause inelastic behavior to begin is reached or exceeded. And the last one is the elastic behavior in which the moment strength MCR is controlled by inelastic buckling. So for the elastic lateral torsional buckling moment MCR, or also known as the critical moment, we now recall the derived partial differential equation for the elastic lateral torsional buckling, which is this equation. So this above equation may be written in the form written below. So this is the fourth derivative, second derivative, and the constant term as far as the order of differentiation is concerned. So the coefficient therefore may be eliminated or transformed into alpha and beta factor by dividing the whole equation with E times C W, where alpha is now equal to GJ all over 2 ECW, and beta is equal to mo squared phi all over E squared CW IY. So the characteristic roots of that equation may be expressed by using the quadratic formula. And this is the root m squared is equal to alpha plus the square root of beta plus alpha squared. So taking into consideration that your alpha here okay, is equivalent to B in the quadratic equation, and your beta here is equivalent to C in your quadratic equation. Hence, your B over 2 plus or minus square root of B over 2 squared minus C gives you the root of the equation m squared. Okay, so this becomes now your alpha plus or minus square root of alpha squared minus beta, which is this value here in the parentheses. So this becomes a positive beta since your beta here, or you have a minus sign here for your quadratic equation. So this is plus. And hence your final root m will simply be the square root of this value. So for simplicity of results, we use the positive value of alpha in this derivation of the root. Hence, by simply substituting the boundary condition for a simply supported, noting that for simple supports, there is no twist involved, but still the section is free to warp. Okay, in such case, the values of the angle of twist at the boundaries z equals 0 and z equals L will be equivalent to 0, and the second derivative of your angle of twist will also become 0, noting that there is no twisting happening at the boundaries, neither torque is happening on the boundaries. Solving the above problem using boundary value method will finally give you a solution for the critical moment MCR in this form. So I did not give you the details of this. I just want you to look into Salmon Johnson's book to have a better understanding on how this critical moment was derived. So the final equation for a critical moment is given here in this formula, and this formula is the basis for the LRFD equations we will be using later. So for the LRFD approach. On I-shaped beams subjected to strong axis of bending, the design criteria, according to AISCB 3.3, may now be stated to be phi mn, or simply phi b mn, greater or equal to mu, where phi b is the 0.90 and mn is the nominal moment. So this mu is the factored service load as given in your load combination list for LRFD. Whether or not plastic moment strength is reached, failure will be on one of the following modes. So as described earlier above, we have the plastic, the inelastic. Okay, these two are the inelastic, case 2 and 3, and the elastic mode. So, in analogy with the compactness requirement, we have the compact or the plastic, the compact, the semi-compact, and the slender mode. Okay, so here we have simply defined it on the basis of plasticity and elasticity since we are directly concerned with the behavior upon which the bracing system are placed. So for case 1, when the bracing is sufficient, there will be plastic moment capacity along with the large plastic rotation capacity, where the rotation may be greater than or equal to 3. So take note that in this case, the section must be compact to prevent local buckling, and the lateral bracing must be provided where your brace length is less than your length considering plastic deformation to be achieved. Okay, so here is now your rotation, moment rotation, or moment curvature relationship. Your range of rotation here is equivalent to your plastic rotation multiplied by R. Okay, so this is the required rotation capacity for case 1. If you talk of the plastic moment versus the average flange strain, simply convert this in terms of strain, epsilon, instead of plastic rotation, theta p. So for the LPD derived and provided by the code, the limiting length for plastic deformation to happen is actually given with the ratio of LPD over RY less than or equal to this value. Okay, or simply this value here where Fy is in KSI. So this is a simpler limiting expression compared to this one here. Just take note that this term is within the parentheses, so we can simply distribute the value of E over Fy to yield this result. So you may use M2 instead of MP according to AISC Appendix 1.7 because M2 is equal to MP under case 1. Okay, so M2 is equal to MP under case 1. M2 is the bigger moment, always greater than M1. So for the case 2 scenario, the plastic moment is rich but with relatively little rotation. And the plastic lateral brace length is given by a simpler formula 300 over the square root of Fy. So note that the section must be compact to prevent local buckling. Again, and the lateral bracing must be provided such that your brace length is less than your plastic brace limit LP. So case 3, the lateral torsional buckling of compact section may occur in the inelastic range where MP, which is greater than MN and greater or equal to MR. So noting that the section must be compact to prevent local buckling. Lateral bracing must be provided where LP is less than LB is less than LR, or simply your brace length is in between the plastic lateral brace limit and the critical lateral brace limit LR. So the nominal strength moment Mn is then a linear function of the lateral torsional buckling strength. Thus, Mr is taken to be 70% of your yield moment. So for the determination of Mn, we simply take a look at the moment versus lateral brace length graph, on which your MP is your LP is your MR, okay, and this is your LR. So take note that in case 3, you are actually falling within this straight line, which can be interpreted in terms of the formula, interpolative formula given here. And an inclusion of what you call a moment gradient coefficient is given in terms of CV, which increases the value of your nominal capacity depending on the shape of the moment diagram. So the mode into which your moment varies with your beam length actually gives you a value of CB for a possible increase in the value of Mn, but not to exceed your plastic moment. So this equation now simply is an interpolation equation obtained from the values MP, MR, LP, and LR. So note of the parameters involved, Fy, Sx, Ix, and D are all the same parameters we are using another a formula uh, in steel design. And the length LR is obtained by simply equating your residual or remaining moment MR, which is 0.70 FYSX, and your MCR, which is this equation here, as derived from the above equation. Okay, so derived from this equation above. They are made equivalent such that by simply solving the value of L, we come up with the value of your critical length, brace length LR, equivalent to this formula here. So I'm just trying to give you an idea on where the formulas were obtained to have a better understanding of on how this formula works. Now, in case there are situations where you need to modify some parameters, you can easily go over this formula to come up with a more suiting analytical approach to specific problems. Okay, so here an RTS was introduced now. So this has something to do with the radius, no? Radius of gyration for this laterally torsionally buckled section. Okay, and this is equivalent to the square root of IY all over SX. So another new parameter here is the C parameter, which is simply a dimensionless factor equivalent to 1 for a doubly symmetric I shape, and HO over 2 square root of IY over CW for a single symmetric I shape such as the channel shape. And HO is simply the distance between the centroid of the two flanges. We are using an English unit here, therefore your value of HO must be in inches. So RTS can also be approximated by using this formula. In case you don't know the values of your IY and CW. So for the case 4 scenario, the general limit state where nominal strength, moment strength Mn occurs in the inelastic range, and that is MP greater than MM greater than MR, noting some of the conditions. Number 1, this is very uncommon for road shapes because road shapes are designed and manufactured to situate that the inelastic failure or failure in the inelastic range may not happen due to compactness. Number 2, lateral bracing must be provided where LP less than LB less than LR is satisfied. Okay, so meaning to say that your brace length must be in between the length into which plastic behavior will happen and the critical length into which your buckling due to lateral torsional effect may happen. So number 3, the nominal strength Mn is a linear function of the lateral torsional buckling strength, thus taking your residual moment equal to 70% of Fy as x. Number 4, the flanges are within the non-compact limits. Web backlink, local backlink are excluded in this case. Okay, we are just talking of the flanges as the more critical element since it is unstiffened. So number 5, lateral bracing must be provided such that LP is less than LB less than LR. Okay, and the nominal strength Mn is simply a linear function of the lateral torsional backlink strength. Thus, Mr is again equivalent to 70% Fy times Sx. So this is just a repeated, no? So nagkamali tayo dito. This 5 and 6 was just a repetition of these two here. So we only have 4. So we disregard this, no? So it's just a repetition of this second and third here. So the strength, therefore, is simply a linear interpolation of again your moment versus length. So here we have only one possibility of failure, which is the lateral torsional backlink failure, since we are considering here a compact scenario. Okay, but in here we have to compare two cases. One is the case between Mn and LP, and the other one case is between Mn and lambda P. Okay, so again we're talking here of the flange only. Okay, that's why this is lambda PF. So for the non-compact case, or the requirement on compactness, and this is the requirement for lateral bracing. We compare the two such that your governing nominal moment capacity is chosen to be the smaller, of course, of the two. Take note again of the existence of a moment gradient CB here, while in the compactness case or the compactness requirement, there is no moment gradient coefficient used. So other parameters within the equation of inelastic LTB are of the same case for case 3. And for your case 5, this is now your elastic LTB scenario. You are now forced to get your critical moment MCR. Okay, so take note that your MR in this case is equivalent to 70% of FYSX. And the conditions into which this case 5 is considered, it falls on your lambda being greater than the non-compact range, okay, lambda R, both for the flange and the web. and all the other slender elements. So MCR is now equivalent simply with your FCR multiplied by SX, where FCR is given in this formula. No? So simply CB pi over L SX. So take note that the SX there was just introduced to compute back FCR in terms of FCR. MCR rather. Okay, so parang tinanggal ko lang yung SX doon, nilagay ko sa ilalim para magkaroon lang ako ng representation of the critical stress, critical buckling stress. So using the property RTS and HO defined previously, FCR now can be transformed into this equation. Okay, so the properties CW and the GJ properties being converted into an RTS value and the C value, which is the same as that in the previous case. And the nominal strength is therefore this one here. So for the moment gradient CB, which is the modification factor for non-uniform bending moment, variation for a beam segment laterally embraced except at the segment ends, we have two formulas, no? So we have the old formula and the 1993 formula, which is also quite old, but it was updated on ASC 2005, where the term CB is multiplied by a modification factor RM. So in the old 1993, the RM is the one that was just missing. Okay, it was added on AISC 2005. So CB has a minimum value of 1.0 and a maximum value of 3.0 for this case, and CB for this case is always less than, greater or equal to 1.0. So this is greater or equal to 1.0. So which formula to use depends on how you qualify the two formula. This formula is actually a parabolic formula in the ratio, in terms of the ratio of M1 and M2. And this formula is also a nonlinear formula, which has something to do with the moments. Okay, so all the moments here are actually derived from the moment gradient or the moment graph. We need the moments at the 1/4 your brace length, 1/2 your brace length, and your 3/4 of brace length. So these are computed at the quarter points. And of course, you have to choose the maximum of them. So we refer here on the absolute value of the moment. Okay, while here we only have two moments. Okay, so these are the end moments, where M1 is the lower moment and M2 is the bigger moment. Note that Rm is a reduction factor when the section is singly symmetric in reverse curvature bending. So AISCF-1 is the basis of this formula, and this formula is more accurate when the embrace segment has a nonlinear moment variation. So this is the reason why the AISC updated for us to be able to use the more appropriate formula for our CB value. Okay, but if you don't want to overestimate your moment, you simply use CB equivalent to 1. So for practical reasons and more conservative approach, you use CB equals 1. Okay, so that ends my discussion on uh, the four cases. Other divide this into several sub cases, but in my presentation, I only use four cases to uh, use as a basis for my computation of on the moment capacity. Thank you very much, and I'll see you in the next video.